Hello, everyone. My name is David Deng, and I'm the application scientist at ChemAxon based in Boston. Today, I'd like to do a little demonstration of the Markush technology. So, Markush structures are widely used in chemical patents. It is very useful because it can define a very large chemical space. However, it can also be very flexible. That's why some people may feel intimidated and feel like Markush technology may be something too distant, too far away from them. But actually, that's not true. Markush technology can be used in many different areas, from, for example, R group decomposition to virtual library enumeration, or even just a simple structure search. You can use Markush technology. So today, I'd like to do some demonstration to show how Markush can help your daily work. So, like I mentioned, Markush structures are usually used in chemical patent. Here, I show a very simple Markush structure in a chemical patent. This one has 4 R groups, and the definition of these R groups are described in this paper, in this patent. So, to start our demonstration, I like to begin from this patent and first extract all the exemplified structures from this patent. There are many ways to do this. In fact, I did another webinar back in March about our naming technologies and how we expanded to extract structure information from documents. And that is particularly designed for patent analysis because not only works on non-text PDF, it also returns the location of the structure information in that patent. And that product is called document to structure. If you have the patent PDF file, you can simply use document to structure to open this PDF, and then the structures will be returned. But of course, patent can be a long document, so the process time can be a few minutes. And today we don't have a lot of time, so we're going to take a little shortcut. We also set up a free web service called chemicalize.org. I also introduced that back in my March webinar. And it's very useful to extract chemical information from web pages and documents. And if you can find the full text of this patent online, it's actually faster than document to structure. So what I'm going to do is, first, I go back to this patent, and I like to Google this patent number. So I copy it and go to Google and simply do a search. And I'm just going to click the first result. And here you see an option. You can view this patent and USPTO. I click that. And as you can see, here is the patent full text. And then it's easy. I can simply copy the URL of this page. I know it's a very long one, but you can still copy it. And go to Chemicalize, paste, and click Web Page Viewer. And Chemicalize will go to that web page and look for any chemical information. It could be a chemical name, or a SMILES, or INCHI, or CAS number, and convert them to structures. As you can see, if you move the mouse next to a chemical name, the structure would be displayed. And all the structures are actually summarized on top and shows how many times it appeared in this document. And if I click on a particular structure, it goes to the first occurrence of this name or other information associated with this structure. If I keep clicking, it goes to the next occurrence. So it's very easy to navigate this web page. But for now, I simply want to download all these structures for my analysis. And we have an option here called Download Structures. It has 268 structures total. If you click that, you'll be able to download these structures in 5 different formats. So you can save to your computer, and then I imported these structures to Jenkins, which is our database management tool. And I'll do the rest of the Markush demonstration in Jenkins. So now, as you can see, we have all the 268 structures imported into Jenkins. Of course, these are all the structures appear in that patent document. It could be a solvent like ethanol. And most of them are not so interesting to us. What we are interested are the exemplified structures. So we can quickly do a filtering to extract the exemplified structures. This is, again, the Markush core. As you can see, it has this scaffold. So what I'm going to do is I can quickly do a substructure search. Just go to Query and sketch a substructure using Marvin. We also had another webinar back in, I believe, in August about Marvin, using Marvin to draw structures. You probably know there's a lot of shortcuts and tricks. For example, if I want to add a double bond on the keyboard, I can just press 2 or 3 for triple bond, 1 for single bond. If I want to change an atom, I can simply click the atom letter. For example, change this to oxygen. I can just click O and nitrogen. I said this is query, and as you can see, you find 67 structures that share this scaffold, and these are the exemplified structures in this patent. As I mentioned earlier, Markush technology can be used in a simple structure search. So here I only sketched a very simple substructure query, but you can also add more advanced features to this query. For example, well, actually, let's review some of the variation you can add to the query. As you can see, you can add many different variations. We all call them the Markush variations. For example, you can specify a certain atom. It can be any atom, or a metal atom, or a heteroatom. You can also specify whether this atom has to be on a ring or in a chain, and also the stereochemistry, whether it's an aromatic ring or it's non-aromatic features. You can also specify how many substitutions it has to have at certain location, also how many hydrogens it has to have, and also how many ring bonds that's connected to this atom. You can also add different topology features to the bond. You can say it has to be a ring or a chain bond, or it could be, for example, single or double bond, or it can be any bond. And you can also add position variation bond. In this case, this OH group can connect to any of these 3 locations. And the query can even be a simple Markush structures. You can sketch the core and specify the definition of these R groups, and the search will use all possible combinations for the structure search. So let's do a little bit of variation of our query. So for example, I want to say here it has to have 3 substitution bonds. So I go to click the periodical table and go to Advanced. As you can see here, you can add different variations to the query. You can say, what's the ring size, how many ring counts, different connections. What we need is substitution count. So I click that. If you click here, when it says S star, that means it just has the connections as shown. I click, that means S0, that means there's no substitution. 1, 2, I want it to be 3, 2, 3. So now this query says Here, it has to have 3 substitutions. I set that as query and do another search. As you can see, now we have 65 hits instead. And 2 hits were missing. If you want to find out why they're missing, any search you did in Jenkins are saved. So we can go to listen query. As you can see, I did one search at 10:09 a.m., 67 hits. 3 minutes later, the second search only returned 65. And I want to find out why. What are the 2 missing hits? I can highlight these, select these 2 lists, and click. As you can see here, you can do different combination of the hit result. You could choose the intersection, a union, or different ones. So what I need is those that in the second search result, but not in the first one. As you can see, this one shows the 2 missing results. As you can see here, it only has two bounds. That's why these 2 hits are not included in our second search. Okay. Now let's go back to the full list. Well, that's substructure search. And what if I want to say, now we have the Markush core, and I know there are 4 R groups. I want to figure out what the R groups can be for these 67 exemplified structures. To do that, I can simply do a R group decomposition. So let's go back to instance Jenkins. Now, I will sketch the same Markush structures. To add an R group, I can simply move my mouse here and on the keyboard press R1, R2, R3, and R4. Just want to make sure the numbers are consistent with Markush structure, and it is. Instead, this query and now run. The search only find 1 structure that's matching this Markush core. Of course, that's not correct. The reason is, we go back to query and right-click, choose option. The default says an R atom can only match a group. An actual group cannot match a hydrogen. But in this case, we do want it to match hydrogen. So I click group or hydrogen. Okay. And run this again. As you see, again, he found the 67 structures we found earlier. And all these structures are dissected. It shows the R1, R2, R3, and R4. You can choose to only show the structure or only show the R groups or show the structures and the R group decomposition result. And in this case, the R groups are combined together. If you want to separate the R groups into different columns, you can click Copy to R group table and enter another data tree name, and these R group results will be copied to another data tree. I already copied here. As you can see, now the R groups are separate into different columns, and you can also move them around and do different combinations for your analysis. So this is how to do R group decomposition in instance Jenkins. Now we have the R group definitions for R1, R2, R3, and 4. Now I want to generate a Markush structure, basically putting together all the R1 definition together, R2 together, R3, and R4. To do that, you can simply do it with 3 clicks. The first click this column to highlight the R group decomposition result. Second click, chemistry. And as you can see, there is a generate Markush structure option that will be our final click. As you can see, we have the original Markush core here. You can choose just to display that. And all the R1, R2, and R3, R4, all the results from R group decomposition are combined. And now we have a new Markush structure with all these options. As you can see, R3 and R4 have a lot less definitions than R1 and R2. Now we have this new Markush structures. You can also use our Markush technology to enumerate the whole chemical space. To do that, simply go to Calculation and Markush Enumeration. Here you have the option to just calculate the size of the library, or you can do actual enumeration. So if I choose only to calculate the library size, it shows the total numbers of structures in this space is a little over 4,000. This is a lot bigger than 67 is because now we can have all the different combinations. And if I want to enumerate this, again, I can just choose enumeration. But before I enumerate the structure, I want to expand this chemical space a little bit, because in this case, R4, for example, only have 3 different fragments. I want to add more to it. And then you can use our Markush technology to add new fragments. So let's quickly go over what variation you can use to sketch a Markush structure. You can have as many as R groups as you want. And R groups can have multiple attachment points, and there could be R groups underneath R groups, so they can be nested. You can also have different atoms at one location. In this case, this atom can be either carbon, nitrogen, or oxygen. Or you can have, again, different bonds at one location. You can have position variation bonds. You can also add link nodes and repetition units. And you can also add the so-called homology groups. You probably, if you're familiar with Quastel MMS and CAS STN, they use different terms. In Quastel, they call it superatoms. In STN, they call it generic definitions. But it's basically the same thing, to use a pseudo-atom to define a generic group. For example, CHK here means it could be any RQ group. HET is hetero-ring, monocyclic. And you can also add properties to this homology group. For example, in this cycle RQ group, it had to be monocyclic, 3 to 7 carbons, and saturated ring. So you can add all these different variations when you sketch a Markush structure. So let's go back to Instant Jenkins. And I like to add a new definition to R4. So first, I like to add this to R4. I highlight it, and on the keyboard press R4, and now this is added to the R4 group. And I also need to add a attachment point like the hydrogen, iodine, and methyl. So now I add a new fragment to R4. And now I want to add new variations to it. For example, I want to have different atoms at the same group, at the same location. Then I just click the periodical table and click atom list. Choose multiple atoms. As you can see, my mouse has changed to this. If you click on this atom, then this atom can be either carbon or nitrogen. I can also change this bond to either a single or double bond. And there's actually a shortcut for that. As I said, if you click 1, that's single, 2 is double, and 3 is triple. And if you, on the keyboard, press 1, 2, then that means it could be either single or double bond. Then I want to add a position variation bond. I select multiple locations, right-click, add position variation bond. Now this methyl group could be connected to either of these three locations, any of these locations. And then, if I want to add a link node at this location, I right-click and choose link node 1 to 3. And here, this location could be 1, 2, or 3 covered. As I mentioned, you can also add homology group to it. So you can go to the periodical table and click Advanced. All the homology group options are listed here. So for example, I can click cycloarchaeol group, and you can right-click and edit the format. So I can say this has to be monocyclic, 3 to 7 carbon, and saturated. Now I want to add another R group to this fragment, R5. So we have a new R group, R5. And to make it a little different, I want to add another connection to R5. So R5 now have 2 bonds connecting to it. And this is R5. As you can see, after I add this fragment to R5, here it immediately add 2 labels to the 2 bonds, indicating there are 2 connection points, and you actually have to define both of them. So now I click the first atom. This is the first attachment point, and the next one is the second connection point. If I change my mind, I want to switch these 2, I can just right-click on the attachment point and change it to 1, and the other one automatically changed to 2. And now we have a much larger chemical space because we add all these different variations to the Markush structure. And I can do calculation, Markush enumeration. Let's just see how many structures there are. Now there's almost 150,000 structures, and you can choose sequential enumeration, click OK. In Marvin, it just shows the first 100,000 structures, but you can enumerate the full chemical space using, for example, command line or API. So now after you enumerate all the structures, you can save them to a file and import it back to instant Jenkins, for instance. But if you want to do it simpler, you can save this Markush structure and import it back to instant Jenkins. And you actually will be able to search in this chemical space without enumeration. So you can simply save this Markush structure to a MRV file, and then in instant Jenkins, you can import it back in. So here I imported this Markush structure before this webinar. As you can see, this is the Markush core, and these are all the R groups. And now you can do a structure search in it without enumeration. So I can go to Query, double click, and now let's add a query structure. Query, and run this as a substructure search. As you can see, it shows you not only this structure is in this Markush structure chemical space, it also shows you how it's matching this Markush structure. You can choose only to show the Markush core, or relevant R groups means not only the Markush core, but also the R group definition, the relevant R group definition, together with the part of core that's matching the query. The matching part is highlighted in blue. And you can also choose to show all the R group definitions with the matching part again in blue. So this is how you can use Markush technologies to sketch a Markush structure, to enumerate this Markush structure, and to search in the Markush structure. And together with the tricks I showed you earlier, like the R group decomposition, to generate a Markush structure that I hope all these tricks can help you in your daily work. And as you can see, this is very useful for pattern analysis. In fact, at least one of our users, I'm not going to say which company, but it's one of the top farmers, they bought the Markush technology. So when they want to study a new chemical pattern, they can sketch the Markush structures, and then they can search in the Markush structure to see if their compound overlap with the new pattern. Some people may say, well, does this mean I have to sketch every patent that ever appeared in history? And that's a lot of work. But fortunately, someone already did this work. And by someone, I meant Thomson Reuters. So they have indexed all the Markush structures, and their data is in a proprietary format. Our Markush technology can convert it to, can open this format and display the Markush structure, and then you can do enumeration and search. So we have this collaboration with Thomson Reuters for 7 years now, and now we have the capability to search the complete Markush database that they provide. In fact, we put this Markush structure, this complete database on Amazon Cloud, and then you can connect to Amazon Cloud using Instant JChem, and you can search not only the complete Markush database, but also the exemplified structure, the index, and other text information. So here, what I'm showing you is a much smaller subset of this database. This one only contains 300 patents, so it's for demonstration only. But this is the same interface you see of the full database. In this interface, as you can see, this is the Markush structure of this patent, and these are the exemplified structures of this patent. And there are also other text information. For example, the title, assignee, which is Sanofi Aventis, the patent numbers in this patent family, and also other information like description, mechanism of action, and so forth. And you can also search in this database. So if I go to query, you can double click and sketch a substructure query. And run this query. And since you can quickly do a substructure search within this 300 patents, these are actual patent Markush, so the chemical space can be huge. I've seen chemical space that contains 10 to the 50th structures. But with our Markush technology, you can still do the search in a very short time. Like we're talking, the search is already complete. They find one patent that's matching this query. Again, you can choose to see just the Markush core or Markush core together with these fragments matching the query, and also all R groups with the matching part highlighted in blue. you can also choose to enumerate this Markush structure. So just click enumerate. This is the Markush structure. This is only showing the core. You can choose to do a full enumeration, but the complete chemical space is 10 to the 23rd, so that's too big. But you can choose to generate a subset of it. So in this case, you can do full or random enumeration of 100 structures, and we'll quickly generate these 100 structures for you. Or now we have the query structures here. You can choose to do a Markush reduction, which means the enumerate structures have to have this substructure query. In this case, I do enumerate. As you can see, all these enumerate structures have the substructure query in it. That's highlighted in blue. And when you display, you can also do an alignment. And then, as you can see, the enumerate structures are rotated, so it's in the same orientation as the query. And you can also do post-process filtering. You can add different filters, for example, molecular weight or the Lipinski rule, to only generate the structure that pass your filter. And you can choose to display the structures on the screen or also output it to a file on your computer. So that's how you can do search and enumeration using this database. And we also added many other features. For example, you can export all these exemplified structures from the patent to a file on your computer. You can also retrieve the patent document. Simply click this button. And you can even add notations to the invention, which means after a patent search, if you find, for example, 20 results, and you can add notes to these things. I think this patent is relevant to my project X. For the next one, it could be relevant to my project Y. And then you can go to the notation folder and click notation view. And when you click on one node, it shows all the patents that you labeled that's under this node. And when I demonstrate structure search, I only did a single query search. If you have multiple queries, you can do a batch search in Instant JChem. Simply click Run Batch Search. Then if you have a file on your computer that contains, for example, 100 structures, Instant JChem will use each of these structures for a substructure search, and you'll be able to review the results of each structure in the detailed query result view. So that was how you can use ChemAxon's Markush technology, not only to sketch your own Markush structure and analyze it, and also how you can use it with the Thomson Reuters database. And these are the people who make this project happen. And not only our development team, also other supporting team like the marketing team and application scientists. And if you're wondering where I am right here. I think that's all for today's webinar. So Christian, I'll get back to you. Give this back to you and see if there's any questions I need to answer. Thank you.